So, based on the midterm, so I'm grading a midterm by myself, so I'm gonna take a little bit of time. It's a big class, so it's gonna take some time. And to avoid what happened last time, well, it's kind of a little better. I graded like 10 sheets or something. It's a little better from last time, but I was like surprised. It's almost the same stuff. I didn't even got anything from homework. Everything from. Do you guys notice that everything is from the notes? The spring one I didn't even. Okay, let's talk about the spring one. Do you guys remember we solved in the class one spring that was very difficult? It was something like here, and the spring was here, and it was pulled by, I don't know, like a cord from here. So it was much more complicated. That's what I solved in the class, the work problem. But what I did, I gave you a direct one that there was like something like this, and there's force, and there's a spring. So it was just direct one that has most of the components. I don't know why many people didn't solve it, even it's just one single equation. The work T1, the kinetic energy, plus sum of the work from U1 to U2 is going to be equal to T2, or you can solve it using the conservation of energy. So the conservation of energy is just like the T1 plus V1 plus the non-conservative force is going to be equal to T2 plus V2. V2 is the potential energy that comes from the spring and the gravity, and this one, it's just like you either solve it that way with the work and energy or the conservation of energy. We have done this before. The second problem, the one that it's exactly the same like the one that I solved in the class. I didn't even told you to, like, I give you the velocity, like the one that I solved in the class, I give the velocity up there, and the thing is you have to do a step to get the velocity before the hit. I give you the velocity before the hit right away. I didn't want you to calculate lots of work and energy. So it's almost exactly the same one. And in the class I told you to put the normal and the tangent. So again, I was trying to help you, but nobody put the normal and tangent, just like use this velocity right away. Like anyway, and the thing is with the fluid dynamics, I don't know. Dr. Lin absolutely explained something similar in the class, but for the bus that hits the car and getting the same velocity, we solved it. Two masses are hitting each other, so. Like everything is from the notes, not even from the homeworks or not from even the textbook. It's like exactly the same thing as the notes. Well, with this, you guys, I know like who attend the class is doing good job. Like, because if you don't attend the class, there is no way that you are gonna survive in this class. Like I know the content, the recorded content is too much. So at least when you attend the class, you are retaining some information. So it helps you a little bit when some people is like, oh, that class is recorded, I'm gonna watch the video and then everything's gonna be okay. No, it's not gonna be okay. Because it's too much information in the recording to handle. So when you attend the class, you are writing, you are getting some stuff, you are getting some ideas, and watching the recording, I see people like at least half of the class is like solving everything not right. They are just gonna get, I don't know, after the curving, maybe 50%. So, whatever. I said that if you did your best, nobody's gonna fail, but if you didn't do anything, you are gonna fail. No way. I'm not gonna pass anybody from this class if you didn't good in the exam. So you have to do your best. I know that you guys attend the class and do your best, but I'm saying who's gonna watch this video, if you didn't attend the class and don't do some work, the final exam is gonna, is the one that is the final. So that's the final shot. So if you have something missing, you need to work on it, and so that you can catch up with the points that you missed. All right, so I'm gonna start the last chapter in dynamics, which is the rigid body dynamics. What we finish right now, we finish particle dynamics, we finish seismic or structural dynamics, we finish fluid dynamics, and this is the last part, which is the rigid body dynamics. Okay, so for the rigid body dynamics, by the way, what is the difference between particles and rigid bodies? You guys know the difference? Particles is something small, or a body that is, maybe it's something big, but all the body is moving like pure translation by itself. So sometimes we call cars as a bodies, because the same body is moving with the same velocity. Every point on the body is moving with the same velocity. So that's why we have like a big cars like this, and we represent them by one single body. Okay? But the thing is, since they are moving with every point on this car are moving with the same velocity, so we can represent with one single particle. So it doesn't depend on the mass, it depends on the movement. But if I took just one piece in a body, like let's say I took a bar like this, and I told you this bar is moving pure translation, you can deal with this body as a particle. But if every body is having different movement, like this point is moving differently from this, moving differently from this, so you have to deal with this body as a rigid body. So let's start the topic here, chapter 16, rigid body dynamics. So, talking about rigid body dynamics, I'm going to talk about different types of motions that rigid body can do. The motion number one is that translational motion. Let's call it rectilinear translation. And we are going to talk about curvilinear translation. And we are going to talk about fixed axis rotation. And number 4, we are going to talk about general plane motion. Alright, we're talking about all of these. So when the body is going to become rigid body translation, like if you have a bar like this, and this bar is suspended from a hinge or something, and this bar is moving, something like this, that's a rigid body motion. Every point is this body has different velocity. The velocity here is 0, and the more that you go away, this is one has velocity, this point has a velocity. If you have a body like this, and somehow this body made a movement, these 2 points, and this body came here, this point translate from here and translate from here, that's a rigid body motion, okay? So like, let's say this spin, if it's moving translation like this, or a hockey, it's like a goal something, so the whole body is moving as a one body, that's like, we can deal it with a particle. But if your body is something like this, and it's making like this, and this, the inertia is getting into the weight and keep rotating, that's when the rigid body motion is gonna start. Like, we can take an example, a bike. Like, if you have a bike, you have the front wheel, the back wheel, and you have a big gear, and a small gear here, and somehow this bike is moving. Like, let's say the frame of the body is something like this, whatever, the chair or something like that. If this bike is moving, this body as one single body, this bike is a rigid body translation, so that's we can deal with the bike as a particle, because all the bodies in the bike are moving with the same speed. But this bike has lots of rigid body movement. Look at this. This gear is moving. The thing is, you have a battle here or something, and you move this. That's a rigid body fixed axis rotation. And when you do this, this movement gets translated to this gear, and this gear is connected with the big wheel, and the big wheel with the friction on the ground give a speed to the bike. So lots of rigid body motion led to the total translation of the bike. So to get to the whole concept, we have to study the gears motion and how the gears motion is translated to the wheels motion and how the wheels motion is transferred to the whole bike motion, okay? We're gonna study something like this, but I'm gonna give you an idea how the difference between rigid bodies and bar movements. All right, so let's see about rigid bodies. How does the rectilinear translation look like for rigid bodies? Let's say that we have a body like this, all right? And this is point A and this is point B. A and B. So for a rigid body to have a rectilinear translation, so it should move on the same line, and this point should come here. So point A and point P, and this is the VA, and this is the VP. And to make a rigid body translation, VA should be equal to VB in magnitude and direction. So the point here and the point here, to make a rigid body translation, the velocity at any point on the body should be the same. That's how I make it translation. Because if the velocity on the top is less than here, it's gonna make like this. It's gonna rotate. So to be a rigid body translation or rectilinear translation, the velocity at any single point should be the same. So I'm saying here, velocity vectors are equal at every point and equal in magnitude and having the same direction and are parallel. Okay, so that's the rigid body translation. How about curvilinear translation? Let's say same body here. Curvilinear translation, like if you have the same 2 points, so they are gonna move on a curve, something like this. By the way, the VA, and this is VB, and let's say my body came here, and this is the new point, so let's say that this is VA1 and this is VB1. This is gonna be VA2 and this is gonna be VB2. So for rigid body curvilinear translation, VA1 should be equal to VA2 and VB1 should be equal to VB2. But the thing is, for curvilinear translation, there is like normal acceleration, okay? Like the normal acceleration is more than 0. Why? Because your rigid body, let's say, is moving on a curve. Rigid body is here, and your rigid body came here. By the way, the body doesn't rotate. The bodies translate. If it's rotate, it means it makes like this. There's fixed from one point and rotate about the 1 point. But the thing is, the body's translating, but it's moving on a curve. So your body is moving on the curve like this, and any body that it moves on a curve is gonna have a normal acceleration, a normal. And a normal depends on the radius of the curve. Same thing like the car movement. When you move with a car, it's gonna be, this is actually very close to the car movement. All right, so the thing is, to be a curvilinear translation, the omega of the body is equal to 0. What is the omega? Omega is the radial acceleration. For a body to have a radial acceleration, it has to have a fixed point and keep rotating about the fixed point. Maybe the fixed point at first, like let's say about the gear and the bike. This is fixed here and it's rotating around this, so that's, it has omega because it rotates. This body doesn't have omega, it doesn't rotate about itself, okay? It just moves on a curve. So omega here, because it's a translation. When there's translation, omega is equal to 0. And this one is omega also equal to 0. Omega is the radial velocity. Okay? Alright. So this is for translation. Let's get to fixed axis rotation. How it's look like. For fixed axis rotation, let's say that you have a body like this, a general body, and this body is hinged at a specific point. So if you lift the body, it's gonna fall like this, right? It's gonna rotate around this point, like the same thing like here. This is rotating about this center point. All right, so this body can have an omega. Why? Because it can rotate around any point around the body, so it has a radial velocity and radial acceleration. And if you know the omega of the body, omega for this body is constant, like it have one single omega value. Every point on this body is having the same omega, right? Let's say that it has omega. But the velocity on any point on this body is different. Like if you get the velocity here, it's different from here, it's different from here, it's different from here. Why? Okay, let me make a line here. If you guys remember, the velocity is equal to omega cross product r vector. How does that counted? Let's say, what is the velocity here at this point? 0, right? This point doesn't move. This is where the point, where's the body's hinges, right? The more that you go away from the center here, the more the velocity is increasing. So it's something, here's the velocity here. And it's linear. So here, this is the velocity. Here, this is the velocity. Here, this is the velocity. It depends on what? It depends on r. How far are you from the center of movement? So this r is much smaller. This r is much bigger, and the maximum velocity at the last end. How we can get this? Basically, the velocity is the cross product of omega multiplied by the r vector. Do you guys know what is the cross product is? Okay, do you guys remember what is the dot product? If I multiply omega dot product by r vector, what is the quantity? Scalar or vector? Scalar, right? Dot product gets you scalar. And actually the scalar quantity is the absolute value of omega multiplied by the absolute value of r multiplied by cosine theta, cosine the angle between them. Like let's say omega is that way and r is that way. So you get the theta between two of them and you put it here so you get a quantity, right? But you will tell me, omega is not a vector, omega is like a moment. Do you know how we can get the vector of a rotational quantity? So it's with the right hand rule, okay? So if omega is going that way, you curl your hand with the right hand, not the left hand. So omega is rotating that way, so the direction is in the plane, like it's going inside the plane. You guys got that? Okay, omega is out of the plane and it's rotating that way, so that's the direction of omega. So if I want to write it, so it's going to be something, I'm going to make it go here much more bigger. Alright, so omega is rotating that way. So this is omega. And let's say I want to find the velocity here. So r vector is that way. That's the r vector, right? Then make it r, something like this. Alright, tell me, actually, before I do this point, do you think the velocity is going down or going up? The velocity at this point, knowing that omega is that way. So the velocity is going down, so this body is going to go down, that's going up. So the velocity all here is going to go down. How we can find the direction, you have to do this cross product. Where? This, omega cross r. But we are going to find out how it is. Omega is out of the plane, so if I want to find the direction of the omega, so it's going to be out of the plane. By the way, this is perpendicular to this. I'm trying to do it in a better way, but it's going to be something that is the omega direction. What does that mean? That means that omega is this way and r is this way. Can you guys imagine this? R is this way and this one is going inside the board. Alright, so if you want to do a cross, that's very important. If you don't know how to do this, you will not be able to solve these problems at all. You're going to use 30 or 40 points in the exam. You have to do cross multiplication. If you multiply cross product, you are going to have a vector. But how can I get the direction? The direction is you are going to use your also right hand rule. I'm multiplying omega by r. This is omega and this is r. This is the direction. And if you want to find the direction of the cross product of them, you curl your hand from the first vector omega to the second vector, and the direction is going to be down. If the omega is up, like is like rotating the other way, so the omega is going to be in this direction. It's going to come outside the plane, and this is r. And the velocity is going to be omega from r, and the velocity is going to go up. But since the omega is inside the board, so you are going to make it that way, so the velocity is going down. So the velocity here, that is the v direction, is coming from the cross product of omega multiplied by r. So basically the magnitude of this, like if I want to find the magnitude of the velocity, it's the magnitude of omega multiplied the magnitude of r multiplied by sine theta between the two vectors. Okay? And if theta is 90 degrees, so this one is going to be 1. Okay? Alright, so did you guys understand the right hand rule? So if you have a rotating vector, like let's say I have a body like this, and this body has an omega that way. So can you tell me what is the direction of omega? You're going to use your right hand, and you're going to curl your hand with the direction of omega. So that way, so that means the omega direction is inside the board. That is the omega direction. And the r direction is that way. That is the r vector. So if you want to find the direction of the velocity, you curl your hand from the omega vector to the r vector, because it's omega cross product r, not r cross omega. If it's r cross omega, you will curl your hand from the r to the omega, but that's not that way. It's omega multiplied by r, so the velocity is going that way. This is v. And that makes sense. This body has an omega that way, so the velocity is all are going that way. If the omega is the other way, so it's gonna be, the omega is gonna be out of the plane. That means, like if the omega is that way. So this is gonna be the new omega, and you are gonna curl your hand from the omega to r, and the velocity is gonna be in the other direction, right? You have to manage this right hand rule and try to practice it a lot, so you can know what is the directions of the velocity. All right, so that's for fixed axis rotation. That means the body is fixed at one point. There is one last motion, it's called general plane motion. And general plane motion is a combination between curvilinear translation or translation with fixed axis rotation or something. Like you have a body like this. And this body somehow became like this. That means this point translated here and this point translated came here. How does that can happen? Usually we divide the motions in two motions. One of them translation, like we bring this body from here, translation. Like we get this point here, and this body is gonna be something like this. This is the new point. And then it's going to have fixed axis rotation. So it's a combination between 2 points. Like this body, to come from here to here, versus you have to bring it, like if they are here, you are going to bring it here translation, and then fixed axis rotation. So it's a combination between this and this. Or if the body's here, you are going to bring it with curvilinear translation, like this, and then fixed axis rotation. So it's a combination between two motions, right? Okay, so what we are going to study in details right now is the fixed axis rotation. So let's see how that works. So for fixed axis rotation, let's say that we have a body like this, and this body is connected with a bar, and this bar is hinged here, and this body can't rotate around this axis. So if this body can let's say I'm looking somewhere here. I'm gonna take a section in this body. So this body is gonna be something. This is the center. And if I want to draw this circle, it's going to be something, the 2D plane is going to be something like this. And this body is rotating around this. So let's say the direction of the theta is that way, and omega is that way, and alpha, what is alpha? Alpha, do you guys know what is alpha? Omega is the radial velocity. Alpha is the radial acceleration. Do you guys remember from the chapter 12? Okay. So omega is, and sometimes somebody like body has omega that way, but the alpha in the other way. That means the body is decelerating. That the radial acceleration, it's decelerating. So if they are in different direction, right? Okay. All right. So I'm gonna talk about some quantities for the fixed axis rotation. I'm gonna talk about angular motion, angular position, angular displacement, angular velocity, angular acceleration. That's the quantities that we studied for particles. If you guys remember when we study like Cartesian or when we study the particles, we have been studying the position, the displacement, the velocity, the acceleration, and we studied the speed and the difference between the speed and the velocity. That's what we want to do also for the rigid bodies. So the angular motion, only lines and rigid bodies that can do angular motions. Like angular motions, it needs to be a body that is moving around the point. But if you have a particle, the particle is just one body. It doesn't rotate, okay? If it rotates, or there's a rotate about an axis, it moves it from a particle to be a rigid body. So you only want to have a line so it can't rotate about a single point, okay? So that's what I'm saying for the angular motion. For angular position, is like, let's say, let's say that this body is started at, like let's say I have a point P here, and this point P, if we want to describe the position of B, we need to describe it with a specific axis. So here, I say that point P is at distance or at angle theta from x-axis. So that's what is the angular position at theta. If you guys remember when we described the position, we described the position with S for bodies. Like you have a body here and your origin here and your body's here, so that is the position S. For fixed axis rotation, and you have a point on a surface, you describe the point at what angle. The angle is theta. The angular displacement is d theta. Like let's say this point B is moved from here and it makes this distance. We want to find the difference. This thing, d theta. That's when we talk about displacement. That's what we did, we said ds. Like when we have like a body's moving on a curve and this body's here. So this is, for example, S, and you came here, so this from here is ds. So we have theta and d theta since we have angular quantities. All right, so I said here that the angular position is defined by the angle theta measured from a fixed reference. My fixed reference is x. The angular displacement is d theta, which is the change in the angular position from the initial to the final. How about the angular velocity? What do you guys think about the angular velocity? Can you guys give the definition of the angular velocity? The time rate of change of what? Since we say velocity, velocity is time rate of the change of something. And it's definitely the distance. But since we don't have translational distance, we have angular displacement, so it's the time rate of a change of d theta. how much time did it take you to come from here to here? So it's basically d theta by dt. And d theta dt is the omega. This is the angular velocity. Okay? All right, the angular acceleration, it's the time rate of change of what? Of the velocity. But right now, since we have angular velocity, so it's the time rate of change of the angular velocity. So alpha is d omega dt. And by the way, we can write it differently. The second derivative, yeah, dt squared. Same thing, we have something similar. We had a is dv dt, and it's also d squared s or x dt squared. Same thing applies here. Okay, so that's the omega. All right, so this is the same body that I have, and I know that this body is having an omega, is rotating that way. That is the omega of the body. So if I have a point on this body and I want to find the velocity, I should use this rule. Right? That's what I learned. But how about you tell me, what is the direction of the velocity at this point without using this rule? What do you think this point is going to move? It's going to move, the velocity is going to be that way or the other way? That way, right? Because the omega is going that way, so the velocity is going to be shooting. All the points on this body is going to be shooting that way. But how can I find this? I have to use the rule. Let's say I want to find the acceleration, but to get the acceleration, I need to find the velocity. All right? By the way, right now, all these are omegas and alphas, radial and angular, angular velocity and angular acceleration. But this is linear velocity. So I'm trying to transform it from the angular velocity to the linear velocity. So the angular velocity is how this body is moving around this body, but I want to know what is the v here. I multiply r by the omega. Okay? So that's v omega crossed by r. But the thing is, we have like kind of a general rule for this. I'm going to put it that way. It says that, where is it? All right, so I'm gonna name this RB, and the thing is, you would say, okay, if I want to find the velocity here, I know the omega of this body, omega, and I know the r vector here, so I can multiply the omega by the r vector, and I can find the velocity. You can do this. That's a direct way to do it. But the thing is, you can actually get r from any point on this line. Like actually, you can have r here, and you call this rb. And if you multiply rb vector by omega vector, it's gonna give you the same velocity. Why is this? I'm gonna tell you right now. So if you even take a point here and you get this vector and multiply it by the omega vector, it's gonna give you the same thing. What is rb? rb is a position, is a vector directed from the axis of rotation so it doesn't have to be here, it can be any point on the axis of rotation to point B, the point of interest. Alright, so if you multiply these two quantities together, it's supposed to give you the same thing. The thing is, let's get the quantity. Alright, I'm gonna put this here as an illustration. So that is the vector RB. RB is something like this. That is RB. And theta, since it is rotating around an axis like this, so theta is going up. Sorry, omega. That is omega. It's going that way. Why? Because if you use your right hand rule, the body's, so the omega's, but if it's moving clockwise, it's gonna be down, right? So the thing is, if you cross product the omega with RB, is gonna give you the velocity in the same direction that we are doing here. Like cross omega, like this. By the way, you are going from here to here. Like, let me put it with, this is RB, this is RB, and this is omega. So if you want to find, using the right hand rule, what is the direction of the velocity? So you are going to make your hand like this, and you are going to go from the omega to the r theta. That way. That is omega, and that is r. So you go from here to here, it's going to give you the velocity here. But if omega's down, and you want to right now, this is r, and this is omega's going down, and you want to go right now from omega. By the way, you have to use your right hand, not the left hand. All the time, there's a right hand. And you want to go from r to RB, it's going to give you the velocity in the other direction. Okay, it's going to go that way. All right, okay, let me prove that if you multiply by RB is the same by this one. So the velocity vector V, if I want to get the magnitude, is going to be the magnitude of the omega multiplied by the magnitude of the RB multiplied by sine theta. Right? Okay, so let's find what is the value of RB sine theta. Okay, this is the angle theta that we're looking at, the angle between the two vectors, theta, right? And this angle, can you guys tell me what is this angle? This is 90-degree angle, because that's a body and you cut a section, and this is the vertical thing. And so this is something like this. So this is, because it's a 3D, it shows like this, but this is a 90-degree angle. So the RB sine theta is actually equal to R vector. That's R vector. This is theta. This triangle is something like this. This angle, I don't know, you will tell me, oh, this angle is the one that 90 degree, but it's not that. This is like a 3D thing, and this is the 90-degree angle, and this is like a part of third circle, and this is the angle theta, and for this angle theta, let me put it that way. I'm looking at the 2D section from this. If I take it, you guys imagine what I'm doing in the 3D? That's like, okay, like let's say I cut in this pen right now, but this body, and there's a center inside. So the center inside, to going from the center to the point on the surface is gonna be lying like this. And here, if you cut here, the line is perpendicular to the vertical axis. So this is something like this. If this is R and this is RB, so R is equal to RB sine theta, and this part is RB cosine theta. So RB sine theta is equal to R. So basically, if you cross product, and even if you take a point here, and this point is something like this, it's gonna give you the same thing. It's gonna give you R. Why? Because the theta changes and R changes, and it's gonna give you the same value. So that's why it's a general rule. It's the vector directed from any point on the axis rotation to point B. So you can write it R, you can write it RB, whatever you want. So if we wrote it R, like if I said the velocity V is equal to the omega, cross product by R, and if you want to try the value, the absolute value, sine theta, the angle between r and omega. So if you take this one, r is something, let's look at it like, this is my circle. If this is r, and omega is rotating that way, so omega is going that way, can you guys tell me the angle between omega and r? It's 90 degrees, right? So here, sine theta is sine 90, and it's going to give you 1. So you will end up, the theta is equal to 90 degrees, and this one is going to be equal to 1, and you will end up with omega multiplied by r. Okay? All right, so that's a little bit background about the angles. Let me go for the other side. So the most important rule that we have right now is this one. Velocity is equal to omega multiplied by the r vector. All right, so but this is for now, is still just velocity. What if I want to get acceleration? You guys can tell me how can I get the acceleration from this rule? We did something similar before. What is the acceleration is equal to? The time rate of change of the velocity, right? It is dv vector dt. So I need to take the time derivative of the v vector, which is omega, crossed by r vector. Can you guys differentiate this? What is going to be? Omega and r are two quantities that change over time. So if I want to find the differentiation about them, so you have to differentiate this first and multiply by this, and then this multiplied by the differentiation of this. Like if you have xy equal to z, if you want to find dz dt, you guys remember it was x dy dt plus dx dt multiplied by y, right? So that's the same thing that we want to do here. So you need to get d omega dt multiplied by the r vector plus the omega multiplied by the r vector dt. So you guys know what is the omega dt is? That's the omega dt, right? It is alpha, the angular acceleration. So I have alpha vector multiplied by r vector plus the omega vector multiplied, what is the r dt? The r dt is the velocity, the time rate of the change of the position, the linear position. Okay? So that is the acceleration vector. And the acceleration vector, this component, we call it the tangential component. And this is the normal component. All right? So this one can be written in a different way. We can write A as alpha multiplied by r vector plus omega. By the way, this is not dot. This is all cross products. Because I have cross product here. If it's dot product, it's going to be dot product. This one is cross product. So this one should be cross product, and this one omega cross product v. I already have v is equal to omega multiplied by r. So this is omega cross product r. That's a very, very important rule. I believe all this is in your equation sheet, but you have to understand where these stuff came from. Okay. So this is tangential component, and this is normal component. And that actually makes sense. If you guys remember when we have the acceleration for the linear position, you have A tangent multiplied by R, and then you have something similar here. And by the way, this one is kind of close to the normal acceleration when you have A normal is equal to V squared over rho. V squared we have, it's omega multiplied by R, so omega squared R squared, and you have R here. So if you take this, it's going to be omega squared R. So this is omega R. So it makes sense with the normal acceleration that we learned from before. Do you guys remember? Normal acceleration, velocity squared over rho. And since we have velocity is omega multiplied by R, so you'll have omega squared R squared over rho, which is R. So you'll end up with omega squared dot R. Okay, so that's for the this one, the velocity. This one is the acceleration. This is the most two important rules that we explained until now. The other rules is kind of similar to the particles. If you guys remember, we had before S, V, acceleration. V is ds dt, acceleration is dv dt, and we had another rule, it's called ads equal vdv. And we used all this information to drive the equations in the equation sheet from chapter 12. We have the same thing here. You have theta, you have omega, you have alpha. This is position, linear velocity, linear acceleration. This is angular position, angular velocity, angular acceleration. And omega is d theta dt, and alpha is d omega dt, which is, we can write in a different way, d omega d theta multiplied by d theta dt. How this is equal to this? Because you can cross d theta with d theta and you will end up with d omega dt. Why did I put it that way? Because I can write it as d omega d theta, and d theta dt is another omega. And this is going to give me alpha d theta is equal to omega d omega. This is similar to this. Acceleration multiplied by position, radial acceleration or angular acceleration multiplied by angular position. Angular velocity multiplied by d omega, this is linear velocity multiplied by dt. So it's almost the same rules, but we change it from linear to angular. Okay? Alright, so this is the rules that I have till now. And if I want the reverse part, like the integration part, so let's see this equation. This equation is going to be, you can write it as omega dt equal to d theta. And you can integrate both part from t node to t and from theta node to theta. And at the end of the day, you are going to end up with having theta minus theta node is equal to the integration from t node to t omega dt. We have similar one for the linear. We have s minus s node, the integration of v dt. So same, almost the same thing. Same thing with this. You can integrate this one as well. The integration of alpha d theta and the integration with omega d omega. By the way, you guys can tell me what is the boundaries that I can put here? Is it alpha node at alpha final or theta node at theta final? The integration boundaries is always bounded by the derivatives. So if there is d theta here, so you are going to find theta here. And d omega here, you are going to find omega here. So here's theta node, theta, and here's omega node, omega. And then you will end up, this is when you integrate, this is going to be omega squared over 2, so we're going to have omega squared minus omega node squared equal to the integration theta node alpha d theta. And the same thing here with this one. This equation, you can write it alpha dt equal to d omega and integrate both sides from t node to t and from omega node to omega. By the way, all these equations are in the equation sheet. I'm just showing you how these equations came from. I also showed you before the linear version of it in the first couple weeks of this class. So here, this one is going to be equal to this. It's going to be omega minus omega node integration from t node to t alpha dt. And if you guys remember, we had constant acceleration and variable acceleration. Do you remember that? We had equation of the acceleration is constant and an equation that the acceleration is variable. If the acceleration is constant, And right now we are talking about radial acceleration. I can take alpha out and do the integration, but if alpha is variable, so you have to keep it inside the integration. So as soon as I say in the question that the acceleration is constant, so you can take alpha outside the integration, or you can take it here from here outside the integration. All right, is that clear till now? Is it difficult? A little bit, right? Well, it's a lot of equations, but you have the equations sheet. By the way, all what you have to do is to understand this equation, how to get omega and how to get the direction, and to understand r, how to measure it and how to get the direction. And you understand every component. You don't have to remember. Like for me, I like to memorize the equations, and I like to know where they come from. So, but for you, if you don't want to do this and you want just to use the equation, that's fine. You have to understand what is every component in the equation and how to use it. Like I would give you some information about omega, I would give it to you directly, but I'm not gonna give you r. You have to get it on yourself. Like let's say, okay, this body is like this and is hinged from here and it's supposed to move. And I want you to get the velocity here knowing that the omega is equal to 10. So basically you can measure this distance, let's say it's 50. And let's say you are gonna name some direction. You are gonna say that this is x and y. So this is the I hat, and this is the j hat, and this is the k hat, all right? So omega is in the direction of k hat, but I is in the direction of j hat. So if I multiply them cross product, so I end up with v is going that way in the I hat. So at the end of the day, you know, you are gonna multiply 10 by 15 is gonna give you 150, and the direction is this way in the direction of the I hat. We're gonna solve some examples, but all what I wanna say is, the concept is simple. You just need to know where these components coming from, like omega, r, and here alpha, r, omega, v, all these components. And then how to use these. Same thing that we did with the linear translation. I'm not gonna solve examples today. I'm gonna just exercise with you just to make sure that you understand the concept. Let's say that I have a body like this, a plate, and this plate is hinged somewhere here, okay? And I told you that this plate has an omega in this direction and has alpha in the opposite direction. What does that mean? Omega and alpha are opposite direction. Is the body decelerating or accelerating? Decelerating, right? That means, yeah, it moves that way, but it's slowing down. But if they are in both directions, so it's speeding up. Okay, all right. So let's say at a specific point here, I want you to tell me where is the direction of the velocity, the tangential acceleration, and the normal acceleration. All right, before doing any cross products, first you have to draw a point from the center of rotation to the points that you are looking for. Why? To get the r hat direction, or to get the r direction, r, okay? So, if you know that r is going up, and you know that omega is that way, so doing the right hand rule, that means that omega is inside the board, right? So r is going up and omega is that way. If you want to know the direction of the velocity, so I go from the omega, because that's the number one, and I make my hand, I curl my hand from the omega to r, so the direction of the velocity is that way. This is omega, it's going inside the board. This is the omega. It's going inside, and r is going up, so that red is red and blue is blue. and if you want to do the cross product, you go from omega to r, so the velocity at this point is that way. That is the velocity at A, is in that direction. Does that make sense? Yeah, it makes sense, because omega is moving that way, so all the bodies is moving that way. Okay, let's do another one. Like, let's say, and by the way, it's perpendicular. Let's say I'm interested in point somewhere here. Can you guys tell me what is the velocity direction at point B? It's going to be perpendicular to R, and it's going to be something like this. That is VB. Does that make sense? All right? Still, it's going to go down. That's going up. So omega is going down. If you want the velocity somewhere here, it's going to be perpendicular, and this is, let's say, C. Gonna go that way. Let me ask you, what is the maximum velocity? Is VA or VB or VC? You guys know? The farthest from the center is gonna be the maximum velocity. Why? Because it has the much higher R. R here is bigger. If R gets smaller, if I ask you the velocity at this point is much smaller, how about the velocity at the center? It's zero, because R is zero. So the more that you get away from the center, the more the velocity is increasing. Here is 0, 0, 0, 0, and then getting increased 1, 2, 3 until it gets to the maximum point. Okay, that's for the velocity. What about the acceleration? The acceleration is the same like velocity, but right now it has two components. It has a tangential component and it has a normal component. For the tangential component, it's kind of similar to the velocity, except rather than multiplying by omega, I'm multiplying by alpha. So right now, alpha direction is in that way. So basically, it's coming out of the board. So that's the alpha direction. So right now, alpha is that way, and R is going up. All right. So if I want to find out the direction of the tangential acceleration, I have to curl my hand from alpha and going to R, so it's going that way. So it's in the opposite. Okay, let me put it here. So it's going to be that way. That is the A tangential. And that makes sense, right? If this point is decelerating, definitely the acceleration is in opposite direction from the velocity, because the alpha is going that way. So A tangential is going that way. How about the normal component? Definitely the normal component is always directed to the center. It's something like this. And if you want to find out, you can do it. You can cross product these one by one. You can cross product these two and get a direction. And then once you finish, you cross product by omega. Let's do it. It's going to be difficult, but let's try. So omega multiplied by r is the velocity direction, right? Because we have done this. We get v by multiplying omega by r. And we found the direction of this that way. So if you want to find the direction of the this is the velocity is going that way. Let me write them with the colors. This is VA. By the way, this is coming from this, omega multiplied by velocity, but I put it in this form. So if you multiply omega by v, it's going to give you the direction of the normal acceleration. All right? So right now I have the direction of v. I put it here. How about the direction of omega? Omega is actually going inside the board. Something like this. This is omega inside the board. So this is omega inside the board, and this is v that way. If you want to find the direction of the normal acceleration, you have to multiply omega by v cross product. So you go from omega to v that way, so the normal acceleration is going down. Can you see? And that makes sense. If I have a body, this body is moving that way, the normal acceleration is going that way. Same thing if I'm here, at this point. The tangential acceleration is going to be that way, and the normal acceleration is going to be that way. Here, tangential acceleration is going to be that way, and that is the normal acceleration. Did you guys got that? You have to understand this very, very well. All these directions, okay? Right, I'm gonna do it on another example very quick. A little bit difficult one, but we got this. You have to go home and set and try to find out about all these directions. We're gonna have quiz next week on one of these. And I'm gonna ask you what is the direction of the acceleration, what is the direction of the tangential, the normal. You have to find this by yourself. I'm not gonna have numbers, just directions. Okay, so I'm having a mechanism, something like this, a bar, and this bar is hinged here. And there's another bar like this, connected with a hinge here, and another one connected that way. And I told you one component. I told you that this body has, let's say this is A, and this is B, C, D. And I told you that this has an omega AB in that direction. Map all the velocities on this body. Just velocity. I'm not gonna get to acceleration. It's gonna be the same process, but let's focus only on velocities. Can you tell me what is the velocity of B, if you know omega of this body? By the way, look at this. This body has a fixed axis rotation. Why? Because this center is fixed and this body is moving that way. This one is also has a fixed axis rotation. Can you tell me about the second one, BC? What kind of body motion that it has? Is it rectilinear translation, or is it curvilinear translation, or fixed axis rotation, or general motion? General plane motion. Excellent. Why? Because this body somehow is gonna rotate and is gonna translate at the same time, because it doesn't have this point is not fixed and this point is not fixed. So it's gonna have a combination between translation and rotation, right? But these two bodies are fixed. Okay, let's look at B. What is gonna happen at B? If you know that this omega is gonna go that way, velocity of B is in that direction or that direction? Which one?
Right.
Right. Here, that way. This is VB. Tell me, how about point C? Is it gonna go down or gonna go that way? If this is gonna be pushed, absolutely this part is gonna be going that way. So, can you tell me what is the direction? Like, should I put it like something like this or
No.
something? It's gonna be perpendicular on R, like R that way. It's always perpendicular to R that way. So this is gonna be VC. All right, something like this, and this is going to be the omega of DC. All right. Okay. How about body BC? Do you think it's going to rotate that way or that way? It's going to rotate that way. That is the omega of this body. Does anybody have any question on this? That's like I'm mapping just the velocity. Just I want to know where these bodies are gonna go from each other. So I have this one is gonna be that way. So if I want to find out what is the velocity at VB, I need to find R, and I need this R as a value, and I have omega as a value. I multiply them together. I get the magnitude of V, and I already know the direction. All right. If you want to do them as I, J, K hat, like if you want to put the directionality of each one, we're gonna do this next time. Okay, we're gonna do them like as a vector multiplication. But for me right now, if I know that omega is 10 radian per second, and R is like 5 foot, I multiply 5 by 10 is like 50. So this is 50 foot per second, and in this direction. All right. Okay, so I'm gonna put the notes. Please try to go through this because we are gonna build on this. I'm gonna have applications. Next time I'm gonna solve like maybe 2 or 3 problems on this. So try to understand the concept. The equation is similar to the translational one. Just like look at the equation, you can understand what each component is. Okay, see you guys.